Yes, students, listen. So, just a recall for yesterday class. We started the thermodynamics. So, I already discussed what is a thermodynamics. Thermo means is a heat, and dynamic means is a motion. So, heat of motion. That is a thermodynamics. So, all the units, some new terminology is there. So, similarly, the thermodynamics also new terminology we can use it for that thermodynamics unit. For example, we should not call here the sample. Instead of sample, we can say that is system. Okay, system, surrounding, boundary, everything. So, what is a system means? Which sample we are going to study? That is here system. And except that system, everything is a surrounding. Okay. Then which one is a separate system and surrounding? That is called boundary. Okay, boundary. Then what are the types of system we discussed? Isolated system, open system, closed system. Okay, and homogeneous system, heterogeneous system. Open system means what? Open system means it exchanges both energy as well as matter with the surrounding. That is called open system. Closed system means it exchanges only energy, not matter. That is a closed system. Then isolated system means it won't exchange energy as well as matter with the surrounding. That is isolated system. Okay, and the process also we discussed. Process of the system. Isobaric process, pressure constant, isochoric process, adiabatic process, isothermal process. So isothermal means temperature is same. Adiabatic process means heat doesn't change from the reactant and product. There is no change in the dq. Okay, dq equal to 0. Isobaric process means pressure constant. Isochoric process, volume constant. Okay, then cyclic process. So cyclic process. So everything discussed, and internal energy also. I think internal energy. What is the internal energy? What is the amount of energy? So total amount of energy associated in that system. That is internal energy. For example, E equal to translational, rotational, vibrational, okay, plus electronic level translational. This is the energy of the system. Okay, that is internal energy. And what is a change in internal energy? Delta E equal to product minus reactant. Otherwise, final minus initial. That is delta E, change in internal energy. And heat content of the system, that is enthalpy. What is the enthalpy? Sum of internal energy, then pressure volume change. Sum of internal energy, then pressure volume change. That is called enthalpy, or else heat content of the system. The pressure volume change means what? What is the pressure volume change? That is work done by the system. When the change in the volume, what is the work? We get it from the system. That is a E plus PV. Okay. Either pressure constant means volume change. Volume constant means pressure change. That we discussed yesterday. Okay. Now we go for the laws of thermodynamics. Okay. What are the thermodynamics law? Zero first and second law of thermodynamics. Yes. So here you know the first, what is a law says? What is the first law of thermodynamics? What is the first law of thermodynamics? First law says, it is a very familiar definition, you know well. What is the first law says? Yes, energy can neither be created nor destroyed, but one form of energy is converted into another form of energy. That is the first law of thermodynamics. You write it. First law of thermodynamics. Energy can neither be created. First law of thermodynamics. Okay, energy can neither be created nor destroyed, but it can be converted, right? But it can be converted from one form to another form. From one form to another form. Okay, energy can neither be created nor destroyed, but it can be converted into one form to another form of energy. That is called first law of thermodynamics. What is the first law says? The E2 equal to E1 plus Q minus W. That means the change in internal energy enthalpy delta E equal to Q minus P delta V. The P delta V only is a work done by the system. Just now we discussed what is a enthalpy equation. Delta H equal to delta E plus P delta V. The P delta V is the work done by the system when expansion of volume, right? That much work we obtain from the system when expand the volume of the container, whatever it is. So delta E equal to Q minus P delta V. What is the meaning of this equation? The delta E change in internal energy. That means if we supply the, for example, if we pour the 1 liter of petrol in our vehicle, okay, how much petrol we can use? That is heat supplied to the system. That is 1 liter of petrol, for example. What is the work done by our system? How much kilometer we travel? Okay, we subtract total minus what is the work done equal to change in internal energy. So that much kilometer we travel. Okay. So similarly, what is the total energy we supplied to the system minus what is the work done by our system? Because all the energy the system used in that supplied energy only. Okay. 100 kilojoule per mole you supply to the system means how much work done by the system. You subtract what is the rest of the energy, that is called change in internal energy. Okay, change in internal energy. So delta E equal to Q minus W. That is the meaning. P delta V means how much work we get it from the system, or else how much work done by the system. Okay, and Q means total energy supplied to the system, and delta E is there how much change it's happened in the system. Okay, we calculate how much change is happened in the system means we subtract from the total energy minus how much energy used by the system. Okay, that is delta E equal to Q minus P delta, or else Q minus W. Okay, Q minus W. Actually, the first law, zeroth law of thermodynamics also is there, right? Zeroth law of thermodynamics. Actually, the zeroth law of thermodynamics, they can find it after the first law of thermodynamics only, but their concept, everything is we can match before the first law of thermodynamics. Therefore, they given the zeroth law of thermodynamics. Okay, they find it after the first law only. Okay, you know what is a zeroth law of thermodynamics? What is a zeroth law of thermodynamics? What is the zeroth law of thermodynamics? Zeroth law of thermodynamics, when A equal to B and B equal to C, that means A equal to C, right? When A equal to B, B equal to C means definitely A also equal to C only. That is a zeroth law of thermodynamics. Otherwise, you write it. When two bodies at two different temperature, you write it, zeroth law of thermodynamics. You are following or I am going very fast? Okay. Zeroth law of thermodynamics. When two bodies at two different temperature, when two bodies at two different temperature are brought into contact with each other, after sometimes when two bodies at two different temperature are brought into contact each other, after some time they attain the thermal equilibrium. They attain the thermal equilibrium. Okay, it attained the thermal equilibrium. You know, very simple concept only, zeroth law of thermodynamics. The hot water mixing with the cold water, it attained the thermal equilibrium. Okay, that's why when two different bodies, two different temperature contact each other, after some time it attained the equilibrium. That is the zeroth law of thermodynamics says. Okay, so here, yes, the zeroth law. That's why A equal to B and B equal to C means the A equal to C. It exhibits A equal to C also. That is zeroth law says. Then the second law of thermodynamics. You look at here, before second law of thermodynamics, I discussed only the enthalpy. Yes, enthalpy, internal energy, this kind of term only. But after the second law of thermodynamics only, we go for the, the entropy term, free energy term, Gibbs equation, Helmholtz equation, everything after the second law of thermodynamics. So what is the needs for the second law of thermodynamics? Why we go for the second law of thermodynamics? Or else what it fulfilled the second law of thermodynamics, whatever not explained by the first law of thermodynamics. That we have to know about it. Then only it is what is the use of the second law of thermodynamics. For example, the second law predict the feasibility of the reaction. That means it is possible in the forward direction or reverse direction, like that. It predicts the second law only. The ammonia, preparation of ammonia by Haber process, N2 plus H2 to form a NH3. There the forward direction also possible, reverse direction also possible. But when you get the more product means what we have to do, that we get the information from the second law of thermodynamics only. And the second law also give the information what is a free energy. That means what is a how much energy is available after completion of reaction, or else how much energy is unconverted. Okay, unconverted means we should not get the useful product by this much amount of energy. That information is given by the second law of thermodynamics only. Okay, so and also it predicts the free energy of the reaction. That means you know the randomness, delta S, entropy of the reaction we predict. Okay, write it now. What is the needs of the second law? The second law predicts the feasibility of the process. Second law predicts the feasibility of the reaction. Okay, the reaction is possible or not. If you add N2H2 to get the product or not. Okay, that feasibility we predict based on the Gibbs free energy. Delta G equal to negative means yes, it is feasible. Delta G is positive means not feasible. Okay, that we get it from the second law of thermodynamics. And the second point, it explains that is the rest of the energy we predict. That means it explains why it's not possible to convert heat into equal amount of work. That means 100 kilojoule per mole you supply to the system, but you get the useful work from your system only for 80 kilojoule per mole. The rest of the 20 kilojoule per mole is a waste energy or is unconverted energy, because once the system starts to work, it gets some of the energy, right? That is not given the product of your supplied energy. So therefore it explains why it is not possible to convert heat into an equal amount of work. That's what 100 kilojoule per mole you supply to the system means your system given the 60% of the useful work only. Okay. Similarly, you know, for example, 1 liter of petrol you can use it in your vehicle means at the initial fresh new vehicle means you get the 80 kilometers. After 1 year you get the 60 kilometers. After 2 years maybe 55 kilometers. So what happens? At the first year you get the 80 kilometers. But at the third year you get only the 50 kilometers. What happened at 30 kilometers? Where it lost, right? Where it lost that 30 kilometers. That information is given. Second law of thermodynamics. Okay? Second law of thermodynamics. The third point also here possible. Sometimes handwriting is very poor. Okay. It explains why it is not possible to convert heat into an equal amount of work. How much you supply the heat energy, you should not get the same amount of work from your system. No. Definitely the loss of energy will be there for any reaction, any system. That loss of energy, we get it from the second law of thermodynamics. How much energy it lost from your system. Okay. Then it also predict the direction of energy flow. Direction of energy flow or energy transferred, either forward direction or reverse direction. Okay, we can get it from the second law of thermodynamics. And also direction of spontaneous energy flow and direction of spontaneous process. That means the forward direction is a spontaneous or reverse direction is a spontaneous. Spontaneous means you know very well, without given the external energy, the reaction itself is going and given the product. Without any external energy, it given the product means that is a spontaneous. Non-spontaneous reaction means we have to supply the energy to go for the product side. A equal to B to give the C means the C product, you get it any without external energy, that is a spontaneous. The C product you get some internal energy, input energy is there, that is a non-spontaneous. Okay, right. What is the second law says? Now, write it. Now, second law. Second law. It states that I have to write it. It states that work can always converted into heat, but heat cannot this is second law says. So second law says the work can always be converted into heat. Okay, work can always be converted into heat, but the heat cannot be converted into work. Some of the heat is a loss of energy will be there always. Okay, so heat can be converted, the rest of or remains unavailable or unconverted. That's why I am saying we take a food. Okay, we take a food, but all the food is not converted into energy. The loss of food is there. The loss of energy is there. In our body also, we take a morning food or afternoon food, no, our body is not take all the food, it converted into not energy. The loss of energy will be there. Okay, right. So it states that work can always be converted into heat. That means whatever the work is there, yes, it's converted into heat. But all the heat is not converted into equal amount of work. The loss of heat energy will be there. That is we find it by the second law of thermodynamics. Okay, second law of thermodynamics. For that only, we are introducing a new term, that is the entropy term. We are introducing the entropy here. You know the entropy. Entropy means entropy, the disorderness. Okay, order, not in the order. When entropy increasing, yes, your internal energy also increasing. You get the more useful product when entropy is increasing. Yes, I understood. This is a physical chemistry. It's not like your coordination chemistry. Yes, we have to listen carefully because I don't know when can I take a thermodynamics class. We don't have enough time because the 2nd March or else 3rd week of March we have a sitting again. So before that we have to complete the 2nd as well as 3rd unit. Okay, 2nd as well as 3rd unit. Okay, what is entropy? Entropy of the system. Entropy, you write it. It is measure of degree of disorderness. It is measure of degree of disorderness or randomness. In a molecular system. Okay, what is the disorderness there in the molecules or else the randomness in a molecule we measured, that is the entropy. You know the solid, liquid, gas, where the entropy is more? Gaseous molecule. In the gaseous molecule more entropy because all the molecule is not in the same place, everywhere it's moving. Okay, that's why our surrounding entropy is more than our system entropy, because system entropy is that is a arranged one. The molecules are arranged. Okay, but in the surrounding entropy is not like that. Influence of surrounding is more. Okay, that's why the degradation, everything it's happened very quickly because of randomness is more. Okay, right. So what is a mathematical expression? Delta S equal to Q reversible by T. That means what is a temperature, what is a change in the heat, or else what is a unit per degree or joule per Kelvin per mole of the substance. Okay, per mole of the substance. The change in the entropy of the system is equal to the ratio of heat with the temperature. The ratio of heat with the temperature of the reversible system. Heat with the temperature. Delta S equal to Q reversible by T. What is a unit? Joule per Kelvin per mole of the substance. You take a 1 mole of the substance, you increase the 1 Kelvin. What is a joule? That is delta S unit. Joule per Kelvin per mole of the substance, or else calorie per degree. 1 degree, if you increase the temperature 1 degree, what is the change in the energy? that is unit of entropy. Delta S equal to Q reversible by T. Okay, Q reversible by T. If the delta S system plus delta S surrounding is equal to 0 means that is reversible process. Reversible process. Yes, it is a reversible process only because when equal to 0. Okay, suppose delta S system plus delta S surrounding is greater than 0 means that is irreversible process. Irreversible process. Irreversible process. Sometimes they ask the unit. Please remember unit of the entropy, unit of enthalpy. Okay, they ask in the MCQ question. So entropy is there. Delta S is what is that? State function. Because it is a state function because we measure the entropy at the initial and the final only. Right? What is the change in entropy? Delta S initial what it is, final what it is. Therefore, that is a state function, not path function. On the way we should not measure. At the initial and the final we measure. That's why the entropy is a state function. And delta S entropy is the what is that? Intensive property or extensive property? Yeah, we discussed intensive property and extensive property. Intensive property means what? It does not depend on the amount of the substance. That is, your student listen. Intensive property means intensive property. I told you yesterday itself. Extensive property. Intensive property does not depend on the amount of the substance. So, for example, temperature, pressure, viscosity, that is intensive property. Extensive property means it depends on the amount of the substance. What is the example? Mass, volume, entropy, Gibbs free energy, okay, everything. So delta S is the extensive property. If more quantity is there, entropy is less. Less quantity is there, entropy is more. You know the small gaseous is there means in a particular container volume is fixed means that small molecule it move everywhere, more entropy. The same container number of molecule is more means the restriction is there in that movement of the molecule, therefore entropy is less. So entropy is depend on the amount of the substance, therefore entropy is a extensive property. Okay, entropy is the extensive property. You got it? What I am saying? Entropy is the extensive property. What is the time? 15 minutes more. Okay. Yeah. Change in entropy in reversible process. Reversible process. So what is the change in entropy in the reversible process? You know the reversible process means when a reactant give the product as well as the possible product to reactant. That is a reversible process. Okay. So consider any reaction, A plus B gives C. Okay, isothermal, what is that? Ideal gas at constant temperature. Ideal gas at constant temperature. Okay, when A plus B gives C, that is a reversible process. We are doing the reaction at the ideal gas at constant temperature. So what happened during the expansion? You know that expansion, let the Q be the amount of heat absorbed by the surrounding. Okay, that means when the Q delta S system equal to Q by T, right? Previously just we discussed Q by T. Okay, that absorbed by the system only. Okay, by the system. That means plus amount of heat energy absorbed by the system. Therefore, delta S system equal to Q by T. Q by T, and also the same amount of energy it lost from the surrounding. Then only the system absorbed. Okay, how much energy it absorbed by the system, the same amount of energy it lost from the surrounding. Okay, therefore the surrounding entropy decreasing, system entropy increasing. Therefore what happened? The delta S total equal to delta S system plus delta S surrounding. Okay, therefore this is a plus and this one is a minus. Therefore at net entropy change is 0. That's what I am saying. Plus Q by T, surrounding entropy decreasing, therefore minus Q by T. At the net entropy change in your total entropy is 0. It cancels 0 for the reversible reaction. In the reversible reaction, what is a total entropy change? That is delta S equal to 0. Total entropy change in a reversible system equal to 0, because how much energy it absorbed by the system, that same amount of energy it lost from the surrounding. Therefore total entropy change is equal to 0. That is a reversible system. That means nothing will happen in the entropy. Okay, right. The same change in entropy, entropy change in irreversible system. Irreversible system, it change. Entropy change in irreversible system. If you consider we are doing the reaction at the A plus B gives C product. Okay, that is a irreversible reaction. A plus B gives product of C. Product of C. So here what happened? The system temperature is high, then surrounding temperature is low. Then only the reaction is irreversible, right? The temperature is higher. So system temperature is high, then the surrounding temperature. Therefore what happened? The surrounding temperature is high, then Q is the heat passes irreversible from the system to surrounding. Because here higher temperature, therefore the heat energy transferred from system to surrounding. Okay, system to surrounding. Understood? Because temperature is high for the system, temperature is low for your surrounding. Okay, temperature is low for surrounding. Therefore, decrease in entropy of the system delta S equal to minus Q by, here two different temperature exhibit, therefore minus Q by T1. This is for system. Similarly, when delta S surrounding equal to plus Q by T2. Q by T2. Because here temperature difference is there. For example, you take a beaker. Okay, you are doing the reaction on the beaker, but the temperature is high than the surrounding. Normal temperature is 23 degrees Celsius, but you are doing the reaction 50 degrees Celsius. Therefore, that is a irreversible reaction. There, the change in the entropy is the system entropy is minus Q by T1 and the surrounding entropy is plus Q by T2. Right? Plus Q by T2. Now, what is a total entropy change? You know already total entropy change equal to system entropy change plus surrounding entropy change. Okay, so system minus Q by T1 plus Q2 by T2. Sorry, here also Q1, Q2. No. Heat doesn't change. Okay. So here the Q is the common, therefore you can take it out. Q is the common, 1 by T2 minus 1 by T1. Otherwise, Q T1 minus T2 divided by delta T. So Q1 T1 minus T2 divided by T1 into T2. T1 into T2. So here what happened in case T1 is greater than T2? T1 is greater than T2 means the whole term becomes positive. The whole term becomes positive. That time delta S total equal to positive. Right? When the total entropy is positive, that means higher means that is feasible reaction. Right? Delta S is positive means feasible reaction. Right? Feasible reaction because entropy is more. When entropy is more, you get the very good heat. From the Gibbs equation also the same conclusion will come, delta G equal to delta H minus T delta S. So here delta S is positive means delta G is negative. Delta G is negative. When delta G is negative, reaction is feasible. Delta G is positive, reaction is not feasible. So that is a next table. That also I give. What is the time? Up to that table I close it. Time? 3:15. Okay, 5 minutes. 3? 8? Time is there, right? Only 5 minutes. equation, just we can plus delta H what happened, delta S what happened, delta G equal to delta H minus T delta S what happened, and conclusion. Okay. So delta H is negative, that is exothermic reaction. Okay, exothermic reaction, here positive, here negative, spontaneous. You close it, the first one. Here, when delta H is negative and delta S is negative, here two different types. One is at low temperature plus at high temperature. What happened here? Spontaneous, here non-spontaneous. Here non-spontaneous. Similarly, when delta H is positive, that is endothermic reaction. Okay, that time delta S is positive. Here two scenario is there. One is positive at high temperature, otherwise negative at low temperature. Okay, negative at low temperature. Delta S is low temperature minus at high temperature. So what happened here? This is a non-spontaneous, this is spontaneous. Okay, spontaneous. The last case is plus endo. Delta H is plus means endothermic reaction. Here negative, here positive. Only forbidden reaction. Forbidden reaction in forward direction. Forward direction. Okay. This is maybe they asked the MCQ question from that table. So delta H is delta S, or what is a delta G? Delta G negative means that is spontaneous. Delta G positive means non-spontaneous. That's it. So delta G negative spontaneous, negative spontaneous, negative spontaneous. Wherever the delta G is positive, that is non-spontaneous. Okay, non-spontaneous. So from that we can come for the conclusion when the reaction is feasible, when the reaction is not feasible. That's it. Okay.